Okay, now we're off on video number 3, and this video is going to be all about refraction. You may recall we studied refraction in the Ripple Tank lab last year. Refraction is the bending of light as opposed to reflection and bouncing of light, and because of refraction you get these very strange optical illusions. This is something you may have seen before, a pencil, for example, sitting in a glass of water. It looks like the pencil is disconnected. What's really happening is that your eye is seeing light coming from the pencil, but the light is moving out of the water into a different media, into air. In the process of moving from one material into another material, the light rays actually bend, and so your brain thinks the material is here, the object's here, but the object's actually a little further down. This is typical if you have an aquarium and you look in a fish tank. You may see fish appear to be in different locations than they actually are. So there are many optical illusions. Here's a really cool picture of a flower in the background. Here's the center of the flower and the leaves. A branch is holding a droplet of water. In fact, it has lots of droplets of water. In each one of those, the droplet of water, the curved transparent materials allowing light to come through the material, bend and form an image. So we'll take a look at lenses in a little bit of detail. Again, another optical illusion or a refraction consequence. Now, some information we talked about before. This is very important. We're going to use this a lot in this unit. The speed of light, again, is 3 times 10 to the 8 meters per second. That's something you should jot down. That's a quantity we need to know. When we talk about light traveling through different media, again, we want to talk about their frequencies as opposed to their wavelengths. They're both important, but the frequency is the key thing. We really want to realize that the color or wavelength of light, or the characteristics of light, are really determined by the frequency, not the wavelength. Now, when we look at our equation, the speed of light is d over t. That's our definition of speed, distance and time. With a wave, it's the wavelength. How far it travels is the wavelength, and the time is called the period of oscillation. And again, that can also be equated to the wavelength and the frequency. Now, refraction, you remember this from last year. The refraction is the bending of light as it passes at an angle from one medium into another of different optical density. The optical density is not the same as the physical density. They're very similar, but this has to do with how the light behaves when it's in a particular material. And specifically, the key thing here is that refraction occurs because the speed of light changes. The speed of light can slow down or speed up depending on what material it's in and what material it's moving through. We have an excellent animation showing you this. This is the same company that did the previous animation on reflection. Now, a couple things are important here. If you look at this picture, and I'll pause this so you can see what's going on here. These blue lines represent the crests, for example, of a plane wave coming in towards a barrier. So we have a crest, the area in between is a trough, a crest, a trough. And so we can see that we have a particular wavelength. The distance from one wave crest to another wave crest is a wavelength. As this wave moves from a low impedance, something that's very easy to move through, into a more optically dense material, something that has more impedance or more resistance, a couple things happen. One thing you can notice immediately is that the wavelength changes. So the wavelength of this particular wave, if it were a color, for example, this might be red. As it traveled into here, you might think that it would change to a different color. But again, it's not the wavelength that matters for the color, it's the frequency. So the wavelength does change. In this case, the wavelength gets less. The other thing that happens is that when I run this again, you'll see that the speed decreases. So if you track along here, you can see it moving at a certain speed. As it travels into something more optically dense, it slows down. Now, this is a little confusing, but it's kind of important we get this. You can kind of imagine an analogy of cars on a highway going 50 miles per hour, separated by, for example, what you're supposed to be, 5 car lengths. Somebody in the front spots a cop, everybody slows down to 30 miles per hour, and the cars get closer together. So here the speed was fast and the cars were spread out. Here they spot the cop, the cars slow down and they get closer together. But if you were standing on the side of the road and watching these cars go by, you would hear them at a certain frequency passing you by. If you stood here and watched the cars go by, you would see that the frequency is the same. And that's very important, because what's happening is the light is passing from one material into another. The speed is changing, the wavelength is changing, but the frequency is staying constant. So light does not change color when we shine it through a piece of glass, for example. If you stand outside the window of your house, you don't see your shirt turning from green inside the house to something like red, or blue outside the house. So wavelengths don't change. The frequency doesn't change, the wavelength does. So again, if we run this animation, now the same thing we talked about before with reflection, we can change the angle of incidence. If I put the normal line in here, it's coming in at an angle of 0. So the angle of incidence is 0 degrees, and the angle of refraction is 0 degrees. But unlike reflection where it bounces off, if I change the angle of incidence, here the angle of incidence is 47, the angle of refraction in this case is 29. It depends upon, and again we'll use the ray model, it depends upon the two media. What are the two materials? So how much bending occurs and how much the speed changes depends upon the two materials in question. Okay, and we may come back to this animation a little bit, see something else that's kind of important. So again, bending occurs as speed changes. Now, if you look at this example, here I've done an example where we're going to look at one situation where we're going from something that has a very low optical intensity, where the waves are traveling very fast, into a material that's more optically dense, where it's going to slow down. And in this case, the waves are going to bend a particular direction. We'll do the mathematics of this a little bit later with an equation. But what happens is that the angle of incidence, again, always measured relative to the normal line, is a certain number. If we go from a fast material into a slower material, the angle of refraction will be smaller. In other words, it's going to bend towards the normal. So the theta I will be greater than the theta R. And again, this is only because we're going from a fast material into a slow material. We'll talk about why in just a second. I'll show you that in just a second. The best analogy, and everybody uses the exact same analogy, is the marching band analogy. So we can imagine a marching band, the trumpet players and the oboe players and all these things are all lined up in rows. As the rows approach, so here's the before picture, as the rows approach, what's going to happen is that this is a material that, for example, it could be blacktop. So this is pavement. And pavement provides very little resistance to somebody marching along. So the people marching along here are walking freely. If they were to go into something more difficult to walk through, like deep grass or mud or something, what would happen is that all these people would slow down, but who would slow down first? Well, the person that's going to hit, because they're coming in at an angle, the person would hit the boundary first would actually slow down first. And the person would hit the boundary second would slow down next, and people hit the boundary third would slow down later. So what happens is the wave, because people hit this at different times, essentially what happens is that the wave gets the bending or changing direction in different sections first. So these waves come forward, this guy slows down, these guys still move at a regular speed, these guys slow down, these guys move at a regular speed, and the effect is that the wave as a whole changes direction. So the wave originally was going this way, and now the wave changes direction this way. Now, how much it changes direction, again, depends upon the different media. So if you go from something very fast and something very slow, you'll see more bending. But this analogy, and you'll see this if you watch the Bozeman, he has an animation that shows it nicely. Now, we just did the situation where we moved from fast to slow. Obviously, if we go the other way around, if the light is traveling through a material that can go very fast, or sorry, excuse me, if it's traveling some material where it's going very slowly and it travels back, for example, from glass into vacuum, it's going to speed up. And so in this case, the light ray will bend away from the normal. So here we had our theta I and my theta refraction. Well, if it's moving from slow to fast, the theta I will be less than the theta R. So the light will bend the other way. And again, we'll have a mathematical equation in just a minute to show you which way and how much. This is the key page. There are 2 or 3 statements here are kind of the key things to understand. The amount of bending is determined by how much the speed changes. So the greater the change in speed, the more bending occurs, or more refraction. The amount of refraction, therefore, is proportional to how much speed change there is. Now, what determines the amount of speed change? Well, it depends upon the materials. We'll come back to that a little bit later. Different materials bend things differently. So here's light traveling through vacuum, empty space. It's going to travel into some material. Now, if it travels into air, it's slowed down hardly at all, and it essentially goes straight through. There might be a tiny bit of bending as it travels into the air, and then a tiny bit of bending as it travels back out of the air, back into vacuum. If we go from vacuum into water, obviously the water is going to be more optically dense, so you'll get more bending towards the normal as it's going into something more dense, and then it bends back the other way as it comes back into vacuum. So it's going to slow down and then come out and speed up. So water has a moderate amount of bending refraction. Diamond has one of the reasons why diamond is so expensive and why it's used for jewelry is because of what it does to light optically. So if we were having light traveling through vacuum and hit diamond, well, diamond bends light a lot. It slows the light down quite a bit, and then the light will speed back up to its original speed as it goes back into vacuum. We're not going to worry about metamaterial behavior. That's not something you need to know. But again, all our angles are measured relative to normal lines. Now, how we do this is a property known as index of refraction. It's essentially a constant for the material. And the index of refraction of some material, n sub x, is a ratio of the speed of light through vacuum, which is a constant, divided by the speed of light through that material. So I'm using x as the material, and c is the speed of light, and v is vacuum. And if you look at this, because the speed of light through vacuum is always 3 times 10 to the 8, and because the light can never go faster than that number, the n value is always going to be greater than 1. So anytime you do an n calculation, n is always greater than 1. If it's air, it's almost exactly 1. If it's diamond, it's 2.42. For other materials, have different constants. And you can do this in the lab. You can actually go in the lab and determine these numbers. So there's a table. We usually give you these numbers. Diamond is 2.42. Water is 1.33. Air, you notice, is almost exactly 1. Zircon, which is the fake diamond, is 1.9. So if you want to find out if your diamond is real or not, you can simply just grab a laser, shoot light through it, and see if your fiance is a bum or not. Glass has different indices of refraction. So these are things that we can find in the lab pretty easily. Now, there's a very simple calculation. If we give us 2 of the 3, if we say the index of refraction of water is 1.33, well, that's the speed of light through vacuum over the speed of light through water. We can then find the speed of light through water. So CW has to equal CV over 1.33. And the key here is that, again, speed of light is a constant. And so water slows light down by a factor of 1.33. So the number we're going to get is always going to be less than the speed of light through vacuum. Okay, so water slows light down a little bit. Now, it turns out, we may discuss this a little bit later, it turns out that the index of refraction is actually a function of frequency or wavelength. So it turns out when we say the index of refraction of glass is some number, that's not really true. The index of refraction of glass or some material may depend upon the color of light we're shooting through. So when we say it's 1.58 for index of refraction, we're saying, well, it's 1.58 for this wavelength. It's 1.58 for this wavelength. So different wavelengths have different indices of refraction. We don't really worry about that. So we'll say glass has a particular index of refraction, but it's really a function of wavelength. And this is why we get dispersion. When we send white light through, the light will actually bend slightly differently because of the index of refraction. Glass is not one number. It's one number for red. It's a different number for orange, yellow, violet. And so we get our familiar Roy G. Biv. This is known as dispersion. Of course, it's the Pink Floyd Dark Side of the Moon album cover, which everybody loves. Now, this is the key law. This is called Snell's law. And this is the mathematical relationship that lets us link the index of refraction of one material and the angle it's coming in that material, and the index of refraction of the other material and the angle it's going out in that material. So this NA sine theta A equals NB sine theta B. Some people use numbers, 1, 1, 2, 2, but I use A's and B's. It doesn't really matter. I always call A the one it's in and B the one it's going into. And again, notice that all of our angles are measured relative to the normal line. So this is known as Snell's law. And again, the quick summary says that as the index of refraction goes up, the bigger the index of refraction, the greater the change in speed, and the greater the change in speed, the greater the amount of bending. Then it's simply a matter of doing calculations, and this is basically plug and plug. We look up values and we say, okay, index of refraction of air is about 1.00, the index of refraction of glass is about 1.50, and again, these vary by material. If I send this light in at 30 degrees, what angle is it going to come out at? Well, the first thing I do is I'm going for something that has a low optical density and to a higher optical density, so I know that it's going to bend towards the normal, because I'm going from N low into something with N high, so I know it's going to slow down. So the speed will decrease, the C will go down, and therefore we're going to have towards the normal. Okay. Now when I do the calculation, we plug in the NA sine theta A and B sine theta B, and we solve for theta B. Just obviously a couple things. Make sure your calculator's in degree mode, and we'll get a number, and that number will be something less than 30. So you do the calculation, and I don't know the numbers, I don't have the calculator here, but let's say the angle comes out to be 18 degrees. That's just an estimate. So that means my angle now will be something less. So instead of the light traveling straight through, the light will bend towards the normal. So Snell's law allows us to do the calculation to get the actual how much it bends. We can bend, again, towards the normal or away from the normal. So sometimes we give the indices and we calculate the angles. Sometimes we can measure the angles and calculate the indices. Again, it's a very simple calculation. Again, I mentioned we can do this in lab, and sometimes there are some lab activities where we actually do this. We'll shoot light with a laser through different materials. There's a lab where I shoot light through a jello. I shoot a laser beam into the jello. We measure the angle of the jello, refracts or bends the light. Jello, as you might suspect, has an index of refraction close to water because it's primarily water and gelatin. And so it turns out the index of refraction of jello is about the same as the index of refraction of water. Okay, I'm going to stop here. I'll add an additional important conversation about partial reflection and internal reflection.